Welcome to today's Explainer. Get ready, because we are looking at a literal David versus Goliath story unfolding right now at the absolute cutting edge of artificial intelligence. You know, for the longest time, the narrative in AI has basically been that you need massive, sprawling corporate monopolies, billions of dollars, and just endless walls of servers to achieve true state-of-the-art breakthroughs. But today, we're diving into a new technical report from a small, incredibly brilliant academic team that has completely flipped that script. I mean, look at what this team managed to pull off. They've built an AI search agent that goes toe-to-toe with the tech giants, and they did it not by throwing mountains of money at the problem, but by fundamentally rethinking the data itself.
It really makes you wonder, does building a frontier AI search agent actually require massive corporate resources? Historically, deep AI search has been what you might call a closed-door game. It's been totally restricted by the sheer immense compute costs of tech giants. Building an agent capable of scouring the web, synthesizing really complex information, and performing long-horizon reasoning, well, that was thought to be a luxury reserved only for the most well-funded companies on the planet. Academic researchers in the open-source community were essentially locked out by this massive barrier to entry. But what if that barrier is just an illusion?
Okay, let's dive into this and look at the typical industry recipe. It's incredibly heavy and resource-intensive. You start with continual pre-training, or CPT, on massive datasets just to absorb raw knowledge. Then you move on to Supervised Fine-Tuning, SFT, teaching it how to actually answer questions. And finally, you run it through incredibly complex reinforcement learning, RL, to polish up its behavior. It's this massive multi-stage pipeline. In contrast, the OpenSeeker methodology strips away all that complexity. Their approach? A simple, single-stage, supervised fine-tuning process. But the catch is the second half of that equation, incredibly high-quality, high-difficulty data. They basically swapped compute complexity for pure data excellence.
Which brings us to our academic challengers, a team of researchers from Shanghai Jietong University. They developed OpenSeeker-v2 to test a genuinely audacious core hypothesis. They believed that data quality and data difficulty could actually act as a total substitute for massive compute power and all those convoluted training pipelines. They wanted to see if they could push the absolute limits of search agents using only a pure SFT baseline. I mean, if they could prove this, it wouldn't just be an academic victory. It would literally be an inspiring blueprint for democratizing AI research across the globe.
Now, to pull this off, the team obviously needed a secret weapon, and that weapon was how they built their training data. They didn't just scrape the web randomly, they engineered a highly specific data synthesis pipeline. They introduced 3 brilliant yet surprisingly simple modifications to how AI training data is generated. Step 1 is scaling graph size, Step 2 is expanding toolsets, and Step 3 is strict low-step filtering. So let's break down exactly what each of these means and why they're so incredibly effective.
First up is scaling the graph size. Think of a knowledge graph kind of like a map of connected information. In standard training, an AI might be given a small, local map to solve a problem. But what the OpenSeeker team did was significantly expand that topological graph size during data generation. By blowing up the size of this map, they injected a much richer, vastly more diverse set of source information into the context. This structurally mandates the AI to learn deep, multi-hop evidence aggregation. It can't just look at one connected dot anymore. It actually has to traverse across multiple nodes to find the answer.
Next up, they expanded the tool set. When an AI agent performs deep research, it relies on tools, right? Things like search engines, calculators, or web page readers. By equipping the OpenSeeker AI with a significantly larger number of available tools during its training, the researchers taught the model to be incredibly versatile. It learned really diverse interaction patterns. It figured out how to leverage complementary tools to solve a wider variety of complex queries. So instead of being a one-trick pony, the AI becomes this flexible problem solver, adapting its strategy based entirely on the specific tools it has at its disposal. Now, this third step is honestly my favorite: strict low-step filtering. Imagine a teacher creating a final exam and deciding to just rip up and throw away all the easy questions. That's essentially what the team did here. They filtered out any training trajectory, any question and answer path that could be resolved in too few tool call steps. If an answer could be found with a quick direct lookup or a shallow keyword match, boom, it was dropped. This establishes a strict minimum difficulty floor for the training set, forcing the model into sustained reasoning and long-horizon information seeking. And this brilliantly illustrates the impact. Notice how the red path for OpenSeeker-v2 stretches much further to the right compared to the blue path of heavier models like RedSearcher. That rightward shift proves that OpenSeeker-v2's training data requires significantly more complex, multi-step reasoning. In fact, OpenSeeker-v2 averages an impressive 64.67 steps per trajectory.
Because it was only fed incredibly long, difficult tasks during training, it actually learned how to handle long, difficult tasks in reality. Which brings us to this jaw-dropping number, 10.6K, 10,600. That is the entire size of their highly condensed training dataset. I mean, in an era where AI models are trained on millions or even billions of data points, unlocking state-of-the-art performance with merely 10,600 training points is practically unheard of. It perfectly validates their hypothesis, though. A tiny amount of flawlessly curated, exceptionally difficult data is vastly superior to a mountain of mediocre data.
Of course, having a clever training method is one thing, but how does this 30 billion parameter academic model actually perform when put to the test? Well, the researchers evaluated OpenSeeker-v2 across 4 highly challenging agentic benchmarks. We've got BrowseComp, its Chinese counterpart BrowseComp-ZH, the incredibly daunting Humanities Last Exam, and XBench. These are basically the absolute proving grounds for frontier AI right now, so let's see how our underdog did.
Now, what's really interesting about this slide is that across the board, you can see the SFT-only model standing taller than the massive industrial models trained with that extensive pipeline we talked about earlier. In dark blue, OpenSeeker-v2 consistently overtakes Tongyi Deep Research, which is shown in light blue. The simple academic baseline didn't just compete here, it decisively outperformed the heavy industrial pipeline.
Let's walk through these hard numbers from the paper to really nail this down. The underdog victory is just undeniable. It edges out the giants on benchmarks like BrowseComp and Humanities Last Exam. But look specifically at BrowseComp-ZH. OpenSeeker scores an incredible 58.1% against Tongyi's 46.7%. That is a massive 11.4% performance gap. These aren't just rounding errors. These are substantial victories achieved entirely through data quality over compute power.
And the story actually gets even better. OpenSeeker-v2 doesn't just beat its direct 30 billion parameter rival, Tongyi Deep Research, it outshines RedSearcher 30B, which is another model trained with a heavy pipeline. Even more astonishing, it holds its own against massive open-source models, beating the colossal DeepSeek v3.1 on certain metrics. It's literally leaving massive 671 billion parameter models sweating in the ring. And it even surpasses closed-source proprietary heavyweights like Claude 4.5 Sonnet, specifically on the BrowseComp benchmark. It is punching so far above its weight class, it's redefining the weight classes entirely.
So the crucial point is this. We are witnessing a genuine paradigm shift. This research completely challenges the deeply ingrained industry assumption that you must have a multi-stage, compute-heavy, incredibly expensive pipeline to build frontier search agents. What the Shanghai Jiao Tong University team has unequivocally proven is that carefully designed data alone, data that structurally enforces multi-hop reasoning and high difficulty, can unlock massive performance gains on its own.
Which immediately begs the question, what's next? I mean, if they achieved this with just 10,600 samples, what happens when they actually scale up? Well, the researchers' future plans involve exactly that. They've noted strong scaling potential and plan to push forward by scaling up the data quantity, the quality, and the diversity. If this is what the baseline looks like, the future iterations of this methodology are going to be incredibly exciting to watch. And perhaps the best part of this entire report is the team's commitment to the broader community. To quote the researchers directly, "We are excited to open source the OpenSeeker-v2 model weights and share our simple yet effective findings to make frontier search agent research more accessible to the community." This isn't just about getting a high score on a benchmark, you know. This breakthrough actively shatters the industry monopoly. By open sourcing the model, they are handing the keys to the castle over to academic researchers and developers everywhere.
So, we'll end today's explainer with a thought to carry with you. We've seen that brilliant, rigorous data synthesis can absolutely topple the advantage of massive, sprawling compute pipelines. The barrier to entry has just been radically lowered. So I have to ask, if simple, high-quality data can truly rival the endless resources of tech monopolies, what incredibly innovative, democratized AI will the open-source community build next? Thanks for joining me on this deep dive, and I'll catch you on the next explainer.